In this tutorial you will learn about the cooling tower. Cooled water is needed for example, air conditioners, manufacturing processes or power generation. A cooling tower is an equipment used to reduce the temperature of a water stream by extracting heat from water and emitting it to the atmosphere. This figure shows a cooling tower. Cooling towers make use of evaporation whereby some of the water is evaporated into a moving air stream and subsequently discharged into the atmosphere. As a result, the remainder of the water is cooled down significantly. Cooling towers are able to lower the water temperatures more than devices that use only air to reject heat, like the radiator in a car, and are therefore more cost-effective and energy efficient. This section gives a basic overview on the cooling tower. Frame and casing. Most towers have structural frames that support the exterior enclosures, casings, motors, fans, and other components. With some smaller designs, such as some glass fiber units, the casing may essentially be the frame. Fill. Most towers employ fills, made of plastic or wood, to facilitate heat transfer by maximizing water and air contact. There are two types of fill. Splash fill. Water falls over successive layers of horizontal splash bars, continuously breaking into smaller droplets, while also wetting the fill surface. Plastic splash fills promote better heat transfer than wood splash fills. Film fill consists of thin, closely spaced plastic surfaces over which the water spreads, forming a thin film in contact with the air. These surfaces may be flat, corrugated, honeycombed, or other patterns. The film type of fill is the more efficient and provides same heat transfer in a smaller volume than the splash fill. Cold water basin. The cold water basin is located at or near the bottom of the tower, and it receives the cooled water that flows down through the tower and fill. The basin usually has a sump or low point for the cold water discharge connection. In many tower designs, the cold water basin is beneath the entire fill. In some forced draft counterflow design, however, the water at the bottom of the fill is channeled to a perimeter trough that functions as the cold water basin. Propeller fans are mounted beneath the fill to blow the air up through the tower. With this design, the tower is mounted on legs, providing easy access to the fans and their motors. Drift eliminators. These capture water droplets entrapped in the air stream that otherwise would be lost to the atmosphere. Air inlet. This is the point of entry for the air entering a tower. The inlet may take up an entire side of a tower, cross-flow design, or be located low on the side or the bottom of the tower, counterflow design. Louvers. Generally, cross-flow towers have inlet louvers. The purpose of louvers is to equalize airflow into the fill and retain the water within the tower. Many counterflow tower designs do not require louvers. Nozzles. These spray water to wet the fill. Uniform water distribution at the top of the fill is essential to achieve proper wetting of the entire fill surface. Nozzles can either be fixed and spray in a round or square patterns, or they can be part of a rotating assembly as found in some circular cross-section towers. Fans. Both axial, propeller type, and centrifugal fans are used in towers. Generally, propeller fans are used in induced draft towers and both propeller and centrifugal fans are found in forced draft towers. Depending upon their size, the type of propeller fans used is either fixed or variable pitch. A fan with non-automatic adjustable pitch blades can be used over a wide kilowatt range because the fan can be adjusted to deliver the desired airflow at the lowest power consumption. Automatic variable pitch blades can vary airflow in response to changing load conditions. This is an schematic of the cooling tower showing all the major components of the cooling tower. The natural draft or hyperbolic cooling tower makes use of the difference in temperature between the ambient air and the hotter air inside the tower. It works as follows. Hot air moves upwards through the tower, because hot air rises. Fresh cool air is drawn into the tower through an air inlet at the bottom. Due to the layout of the tower, no fan is required and there is almost no circulation of hot air that could affect the performance. Concrete is used for the tower shell with a height of up to 200 meters. These cooling towers are mostly only for large heat duties because large concrete structures are expensive. There are two main types of natural draft towers. Cross-flow tower, left figure air is drawn across the falling water and the fill is located outside the tower. Counterflow tower, right figure air is drawn up through the falling water and the fill is therefore located inside the tower, although design depends on specific site conditions. Mechanical draft towers have large fans to force or draw air through circulated water. The water falls downwards over fill surfaces, which help increase the contact time between the water and the air. This helps maximize heat transfer between the two. Cooling rates of mechanical draft towers depend upon various parameters such as fan diameter and speed of operation, fills for system resistance, etc. Mechanical draft towers are available in a large range of capacities. Towers can be either factory built or field erected. For example, concrete towers are only field erected. Many towers are constructed so that they can be grouped together to achieve the desired capacity. Thus, many cooling towers are assemblies of two or more individual cooling towers or cells. The number of cells they have, for example, a 8-cell tower, often refers to such towers. Three types of mechanical draft cooling towers are available. Advantages and disadvantages of each will be explained in the upcoming slides. Forced draft cooling tower. Working principle: air is blown through the tower by a fan located in the air inlet. Advantages: suited for high air resistance due to centrifugal blower fans. Fans are relatively quiet. Disadvantages: recirculation due to high air entry and low air exit velocities, which can be solved by locating towers in plant rooms combined with discharge ducts. Two types of induced draft cooling towers, cross-flow and counter-flow. Advantage: less recirculation than forced draft towers because the speed of exit air is 3 to 4 times higher than entering air. Disadvantage: fans and the motor drive mechanism require weatherproofing against moisture and corrosion because they are in the path of humid exit air. Induced draft counterflow cooling tower. Hot water enters at the top. Air enters bottom and exits at the top. Uses forced and induced draft fans. Induced draft cross-flow cooling tower. Water enters at top and passes over fill. Air enters on one side, single flow tower, or opposite sides, double flow tower. An induced draft fan draws air across fill towards exit at top of tower.